SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. I welcome you to this course Advanced Thermodynamics and Combustions. We are in the module 2 Entropy and Exergy. In this module we have already covered 2 lectures on entropy. So, we are now moving for the third lecture. So, in this lecture we are going to discuss about the following topics, that is entropy data interpretations, entropy equations, entropy balance for closed systems. Of course, we will also discuss about entropy balance for the control volume. Then we will discuss something about entropy as a directionality measure for thermodynamic processes, then something on isentropic processes. So, prior to these lectures we discussed exhaustively the entropy by definitions from the second law and its consequence analysis in variety of systems. In fact, the concept of entropy was introduced through Clausius theorem, and we call this as which is commonly known as Clausius inequality. Now, to make our measurement systems with the viewpoint of thermodynamic analysis for closed systems and control volume, in this lecture we are going to target on the entropy balance equations and how we can form the governing equations for the closed systems and control volume, which is similar for energy analysis that we did using the first law. So, to start with, the first thing that we are going to discuss is that we know what is entropy. So, it is a property of systems which was introduced by the second law. Now, once you know the entropy data, then how you are going to interpret. So, in fact, the word entropy talks about the disorderness of the systems. It allows us to know in a particular directions how a system is moving. So, we know that from the first law energy was introduced and from the second law entropy was introduced, and both energy and entropy are the abstract concepts, and we mainly dealt with energy in our day to day conversions, and for which there is a balance equations, or we call this energy auditing, in which we talk about the energy balance which comes into and out of the systems. Now, similar concept if you want to extend, we are going to do it for the entropy. How we are going to do, that is our main viewpoint. So, now when in a thermodynamic sense, that when you talk about a property, it depends on the states of the systems. For example, if I say that system is at point 1 and another system is at point 2, and if you talk this entropy for the system 1, that is at state point S1, and the system at the point 2, it is S2. So, this is the property dependent. This property is coordinate dependent. So, now by definition of a thermodynamic property, if it changes value between these two states, is independent on the thermodynamic coordinates. So, irrespective of the fact whether I take this path or another path, when I move from system 1 to system 2, So, I say path 1, path 2. In fact, I can also target moving to path 2 in a irreversible path 3. So, path 1 and path 2 we can say they may be reversible, but the path this dotted line shown here, it talk about irreversible path. So, why I am drawing to these things is here is that irrespective of whether we are at state 1 or state 2, whatever path it follows, if it is a thermodynamic property, it is not going to change. This is the by definitions, and this is also true for entropy as well. So, since the entropy is a property, the change of the entropy of the system going from one state to another is same for all the processes. And by Clausius inequality, we know that for an internal reversible processes, the entropy change S2 minus S1 is represented by the integral of dq by t. And if we go for a very small infinitesimal processes, then we say we can write this ds is equal to delta q by t, and this is true when we are dealing with an internal reversible processes. But what Clausius inequality says that always not all the processes will be internally reversible. So, in a general sense he says that this particular relations which is known as Clausius inequality, which is always true, that is ds is always greater than or equal to dq by t, and when it is a reversible processes, the first equation holds good. Now, moving further, there are another viewpoint of this entropy analysis, that when you look the in some senses that in a chemical engineering personnel, they look the entropy evaluation in a different viewpoint, because when we have the chemical reactions, it is always necessary to work with the absolute entropy. So, for that, in order to get S1 or S2, we need to find out the entropy value at, let us say, state 1 will be addition of two parameters. One is reference entropy at a given pressure and temperature or the given thermodynamic conditions, plus the entropy transfer dq by t. So, this is how the entropy of, by definition, what we call as absolute entropy. So, the concept of absolute entropy is given by these equations, where Sx is your reference entropy. Now, in many situations, when you deal with the pure substances, and these pure substances have three different distinct phases, that is solid, liquid and gas, and their representation can be drawn in the property diagrams. Typically, the property diagrams are pressure volume diagram as shown in this figure, or the temperature volume diagrams. So, in this both the diagrams, you can see the dome that constitutes the distinction of three different phases. For example, if you look at this dome, on this dome there is a peak point, and we call this as a critical point, and this critical point essentially distinguishes the two different distinct phases, and there are three different regions. One is liquid, other is vapor. Here also we have liquid and we have vapor, and in between, within this dome, we say liquid plus vapor. So, the important point to be noted here is that for a given coordinates, that means for a given pressure volume or temperature entropy, we can find out the thermodynamic properties of all the parameters in the liquid, regions or liquid plus vapor regions, which is commonly known as two phase regions, and only vapor regions we call it as a superheated regions. And if you want to find out the property value, and in particular in this case we talk entropy, we essentially look for which region we are putting our attentions. So, for example, in this case if a system if I locate a point 1 on this saturation curve, another point and the 2 in this again in the saturation curve, and in this curve we can see the point 1 denotes to a saturated liquid regions and point 2 denotes for the saturated vapor regions. Similarly, in the TS diagram here, and if you want to find out the property value, we also define another parameter which is called as a quality. So, this quality within this dome, that means any value within this dome is decided by its quality. So, we call this as either quality of steam or quality of any substance, maybe any refrigerant. So, for that things the entropy data can be evaluated based on the thermodynamic coordinates. So, more clear pictures is shown here, the temperature entropy diagrams and enthalpy entropy diagrams. And this enthalpy entropy diagrams we normally call this as a molecular diagrams. So, you can see here the in this dome we have saturated liquid regions, we have saturated liquid, we have saturated vapor, and this is demarcated by the critical point Cp. Similarly, in the enthalpy entropy diagram or molecular diagram. So, on this diagram various constant pressure lines, volume lines, pressure enthalpy lines are plotted. So, the entire idea of showing this thing is that while evaluating the data for entropy, one can use these graphical representations to calculate the entropy as a thermodynamic property. And moreover, there are other equations and we call them as entropy equations, and these entropy equations can be effectively used. In fact, all the property data were derived from these entropy equations, and if we can effectively utilize them, then we can find out the various relations. And in particular, for entropy calculations, the ideal choice is the temperature entropy equations, and normally that equation we call as TDS equations. So, let us talk about what this TDS equation is all about and how it is derived for various pure substances. So, let us recall that for a pure and simple compressible substances, we can write down the first law of thermodynamics that involves Q, that is nothing but TDS in terms of entropy. We have du, that is change in the internal energy, and we have PdV, that is flow work or work transfer. Similarly, if you write this internal energy as a function of enthalpy, then the first TDS equations is derived in the form TDS is equal to dH minus VdP. So, these two are the fundamental TDS equations which are useful for evaluation of entropy. Now, if I take on unit mass basis, that means if I say U is equal to small u into m, H is equal to small h into m. So, m is nothing but your mass of the substance. So, on unit mass basis, the entropy equations are reduced in this form. Now, if I want to apply these equations for a saturated liquid to vapor systems, so for these systems we know that pressure is constant. So, the first TDS equations from the first TDS equations we can say that is if you say this TDS is equal to dH minus VdP, and in this for the saturated liquid vapors your P is equal to constant. So, dP goes to 0. So, TdS equations now represented as ds is equal to dH by T, and ds is nothing but difference in between Sg and Sf. So, from the enthalpy informations it is possible to find out what is the entropy change between the from the saturated vapor to saturated liquid region. And then another expressions for an incompressible substance. So, now when I say incompressible substance, we are essentially looking the regions which is typically liquid region. So, in this liquid regions entire property is governed by one parameters. So, from this TdS equations we can rewrite ds is equal to dH. dH we can represent it as Cp times T, that is specific, in this case it is heat capacity or specific heat, and PdV, and since there is this in the incompressible regions there is no change in the density. So, this term vanishes. So, in such cases the entropy equation reduces to S2 minus S1 is equal to Cpt by T dt, and if you take specific heat as a constant, we can say C of T ln T2 into T1 ln T2 by T1. So, this is all about what you do it for the pure substance. Now, we will move to ideal gas, how you are going to use the entropy for the ideal gases. So, for that case we have two states 1 and 2. Now, in this one we say its property or entropy we define as S T2 V2 or S T2 P2, that is point 2, and for point 1 we say S P1 T1 and S T1 V1. So, a system goes from 1 to 2, the change of entropy is written by these two entropy equations, and this is again derived from the two fundamental TdS equations. Okay. So, this is all about how you are going to evaluate entropy. Now, let us see that how we are going to frame a entropy audit for a closed systems. So, by that time by closed system I mean that a system we consider as a closed systems because it contains the same matter and there is no transfer of matter across the system boundary, but the energy interactions is possible. So, there is no mass transfer, but energy interaction is possible. Now, for such a systems we are going to find out what is the entropy balance equations. So, for that we have the fundamental expressions which is called as Clausius inequality. In fact, prior to this we have analyzed this Kelvin-Planck statement and Clausius statements. So, based on this we can say that if I based on their analysis if you consider a closed systems which is executed by two cycles, one is through a irreversible process, other is through reversible process. So, what you see here that a system or process or a system undergoes a change of state from 1 to 2 first in an irreversible process, but it returns to the point 1 again through an reversible process. So, in this way it completes a closed cycle. Now, for this closed cycle we can write this Clausius inequality in this manner that first one system undergoes from 1 to 2 for which there is a boundary heat transfer dq by T, and while return it goes from 2 to 1 in a reversible process, and in this process there is an entropy production, because we need to equalize this Clausius inequality statement. And from this we can write down, and in fact this is nothing but your entropy balance equation. Now, let us evaluate that particular equation in a more elaborate way. That means, here we have shown from initial state to final state, it goes from in an irreversible path and returns to a reversible path. We write this entropy balance equations as S2 minus S1 is equal to delta Q by T with this boundary plus entropy production. So, sigma. So, this is the fundamental equation of what we call as entropy balance equation for a closed systems. Now, if you look at these two terms here, what it says is that the change in the amount of entropy contained within the systems during some time interval is equal to sum of the net amount of entropy transferred across the system boundary in same time interval and the amount of entropy produced within the system in same time interval. In fact, mathematically when we write these equations, the positive or sign or negative sign. So, value of entropy, whether it is a positive, if it is positive which is into the systems, that means in a closed system we say dq when a heat is added into the system, then we say dq is positive, and when heat is taken out from the systems, we say dq is negative. So, this accordingly the change in the entropy is governed by this, the way whether it is added into the system or taken out from the system. Now, we will now look into another viewpoint for the same equations. So, we derived these equations like S2 minus S1 as a integral of dq by t from 1 to 2 for one parameter dq by t, plus there is another parameter sigma. Let us talk about the significance of the sigma. What is this sigma? The sigma is nothing but what we call as entropy production. So, what does this mean? That if a process becomes irreversible, then the entropy is produced within the systems and it cannot be a negative quantity. That is the most important inferences from these entropy equations. So, for an irreversible processes, there is a entropy productions and it is always greater than 0, and there is a possibility that entropy production can be equal to 0 if the system undergoes a reversible process. Now, based on this, the change of entropy from system 1 and 2, either it can be equal to 0 or it has to be greater than 0. There are possibility it can be less than 0. Now, let us see what are the things we are. So, based on this we have these three possibilities. So, the value of entropy production cannot be negative, but the change of system change of entropy of the systems may be positive, may be negative or may be 0. So, we have seen that how it can be positive, how it can be negative, that all depends on whether heat is added into the systems or heat is taken out of the systems. So, from this analysis we can now frame the entropy statement of the second law, which says that it is impossible for any system to operate in a way that entropy is destroyed. That means, entropy cannot be destroyed, it has to be produced always. Now, let us evaluate this entropy balance equation with another viewpoint, that means in terms of solving the problems. One thing is that when you say productions, let us bring the time scale into considerations. What is this time scale into considerations? Now, if you say it is a closed system, and this closed system has a boundary, and across which this dq can be, whether dq can enter or can be positive or negative. So, for this, based on this, we have this entropy balance equations. Now, if this particular closed systems which has a boundary, and it is this boundary is as constant temperature Tb. So, these equations can be rewritten in this manner, because since the temperature is constant, we can bring this out of the integral. So, at constant temperature Tb, these entropy equations can now be written as H2 minus H1 is equal to Q by Tb. Now, on time basis, that means if you say, if you want to calculate what is the rate at which entropy is changing, so you can write in the form of dq ds by dt and is equal to summation of q dot by j Tj plus sigma dot. This summation means there are various ways that this q can come into the systems. So, entire q is governed with summation of all the number of sources that heat enters or comes out of the systems. So, based on that, the statement of entropy balance equation can be written as the time rate of change of entropy of the system is equal to sum of the time rate of entropy to the portion of the boundary whose instantaneous temperature is Tj, and the time rate of entropy productions due to the irreversibility of the systems. Now, having said this entropy balance, we are now able to think about an extended systems or enlarged systems. What does this mean? So, we already say that we have some system, and out of which is not included in the systems, we say its surroundings. Now, this heat interactions is always there between the system and surroundings. What I am looking at is that let us bring entire system and surrounding into one closed loop or closed platform, and we call this as a isolated system. Now, when I say isolated systems, it involves the systems plus surroundings. So, for that energy balance equations we can write for isolated system is equal to 0, total change of energy system and surrounding is 0. Similarly, we can write the entropy balance equations in a different way, that means we can write delta S of isolated systems is equal to delta Q by T plus delta isolated, and this is nothing but delta isolated is nothing but entropy productions. So, by looking this equation closely, we can say that since the isolated systems involve system and surroundings, we can write delta S systems plus delta S surrounding is equal to delta S isolated, and from this equation we can see that this particular term is always greater than 0, because we have already proved that delta is always greater than 0, or it only possibility is that it can be equal to 0. So, this system and surroundings, and in particular we call that as a universe, and for this we can frame this law that delta S universe is always greater than or equal to 0. So, we says that and we says that the entropy is always produced by all actual processes and for which the entropy of the universe is always greater than or equal to 0, or in other words we can say entropy of unisolated systems increases. So, in this case the isolated system is nothing but the universe. Now, let us move to entropy balance equations for the control volume. So, basic difference between a closed systems and control volume is that in a control volume both mass and energy interaction is possible. So, what we have is that in a control volume typically represented by multiple inlets or multiple outlet, as you can see here. So, we may have something entering into the systems, something leaving out of the systems. So, this entering we say some mass that is entering into the systems M1 and M2, and some mass which is M3 and M4 that comes out, and we call this as a control volume. Apart from this there is energy and there is heat interactions Q which from this control volume to the surroundings. So, all these things are possible, and for these things if you want to write down the entropy balance equations, it says that the time rate of change of entropy within the control volume is the sum of 3 terms. First term is entropy transfer accompanying the by mass flow rate into and out of the systems. Second term is rate of entropy transfer at the location of the boundary at which boundary which is located at instantaneous temperature Tj, that means it is a boundary temperature Tj, and that heat entropy transfer is due to heat transfer. And third term involves entropy productions within the control volume due to irreversibility. So, from the analysis of closed systems, if you enlarge it or elaborate it for control volume, we can write down the entropy change for the control volume involving 3 important terms. One is due to first term we see accompanying due to the mass flow rate. So, these 2 terms represent due to mass transfer, or you say mass flow rate, not exactly mass transfer, you say mass flow rate. And this particular first term refers to entropy change due to heat transfer across the system boundary, and the last term is nothing but production. And this production is mainly due to irreversibility. Now, let us move more closely, and this particular slide shows the elaborate version of this differential form of equations for the control volume, and the simplified sense that this particular equation gets simplified for a steady state entropy rate balance. So, what does here mean is that is for a steady state entropy balance we say dSCV by dt is equal to 0. So, based on this entropy balance equation reduces to this form. Now, again when I say that when there is no heat transfer, so that means we say Qj goes to 0, this entire equation reduces to S2 minus S1 is equal to sigma dot Cv by m dot. Here we have assumed that mass flow rate inlet and mass flow rate exit they are same. Further simplifications can be also done for single inlet and single exit control volume at steady state. So, in fact, all these equations are relevant or will be required when you solve the problems. Okay. Now, the another aspect of entropy balance for the control volume is to elaborate the expressions of work transfer and heat transfer for the internal reversible processes. And when you say internal reversible processes, it means they are the internal irreversibilities are absent. So, for an internal reversible processes, these entropy equations we can say this is this S2 minus S1 is equal to 0. So, we start with the first basic expressions Q Cv by m dot is equal to T into S1 S2 minus S1, and this particular term Q dot Cv by m dot is nothing but TdS. So, in turn it gives an impression that if you draw a temperature entropy diagram when the system undergoes from change of state from 1 to 2, and this area under that diagram is nothing but Q by Q Cv, right. Now, so this is what we do if it is an internal reversible process for heat transfer. Now, if this internal reversible process, if there is work transfer expressions, we can rewrite that particular equations that if a system does not have the heat transfer, but it is only work transfer is possible, we can rewrite that equations in this form. So, W dot Cv by m dot is equal to integral of TdS plus H1 minus H2, and here we can say it involves the kinetic energy change and also potential energy change. So, this term is about kinetic energy and potential energy change, and important point that I need to emphasize here that this TdS equations, if you recall, this TdS is equal to du plus Pdv and u is equal to h minus Pv, and when you simplify this we will arrive at Vdp is equal to TdS minus dH, and this is nothing but this particular term Td integral of TdS plus H1 minus H2 is nothing but negative of Vdp, and with no kinetic energy transfer and potential energy transfer, the internal W dot Cv by m becomes integral of Vdp with negative sign, which means if you can draw on a thermodynamic diagram Pv, P pressure volume diagram. So, the process undergoes a change of state from the 1 to 2. So, in fact, there is a, so this is a compression process, and the area under that diagram, that is Vdp, is shown here. So, this is the significance of the entropy balance equation for control volume, how you can represent them in the thermodynamic diagrams. So, last segment of our discussion is about isentropic processes. So, the word isentropic process we mean it is a constant entropy process, That means system undergoes change of state from 1 to 2 without involving change of entropy, and such a process in a TSI diagram and HS diagram is represented here. So, these two are for pure substance. And it is governed by whether this initial state is which region it is, whether it is liquid state or it is maybe mixture of liquid and vapor state. For example, state 1 here it is shown as only vapor state, even 2 also is a vapor state, but 3 is in the liquid plus vapor state, but all of them have same entropy. So, in fact, here also all of them have same entropy. So, it is a ideal choice of temperature entropy diagram or enthalpy entropy diagram is that the vertical line indicates the entropy axis at constant entropy axis. Now, for other situations we can refer the thermodynamic property tables for ideal gas, for maybe thermodynamic properties are referred for pure substances. So, for pure substances entropy calculation is governed through the property tables. Now, for ideal gases we instead of enthalpy entropy diagram, our ideal choice is the temperature entropy diagrams, and in this case we can see that we can have the coordinates of thermodynamic processes 1 and 2. But within this 1 and 2 process we can draw constant volume line, constant pressure line, constant temperature line. Constant temperature line is a horizontal straight line. So, similarly for state point 2 we will have constant volume line, constant pressure lines. But one thing is that this vertical line talk about the constant entropy line, and here in more elaborate expressions for isentropic process is shown in the classical with a classical viewpoint of thermodynamics, where we find the entropy equations, and these entropy equations we can start with these ideal gas situations. For an ideal gas gases with constant specific heat, for an isentropic process we can write down two fundamental equations of entropy equations, fundamental expressions for entropy equations, and from these equations we can recall the expressions for specific heat as a function of K and R. So, K is your, here the K is specific heat ratio, which is Cp by Cv, and R is Cp minus Cv. By putting these equations in these entropy equations, we are able to derive the isentropic relations, that is T2 by T1 is equal to P2 by P1 to the power k minus 1 by k, that is equal to V1 by V2 to the power k minus 1. And fundamental equations that we still use as on today in our classical things, which is Pv to the power gamma is equal to, or k here is equal to constant. So, thermodynamically we represent in this classical diagram pressure and volume on temperature and entropy, and here we draw different constant lines for entropy. So, in this so here the exponent is represented for a constant volume process, n goes to infinity, okay. N can be minus 1, n is equal to 1, then n is equal to 0. So, from these equations we say P v to the power n is equal to constants. So, n can be 0, n can be 1, n goes to infinity, or n can go to k. K is nothing but Cp by Cv. So, this is nothing but your isentropic equations, and which we use in a classical way. So, with this we come to the end of the entropy analysis. So, before you close these lectures, let us solve some simple problems. So, this first problem is about entropy production for closed system. What it says is that we have saturated water at 150 degree centigrades, which is contained in an insulated piston cylinder container assembly. This change of state of this water goes from saturated state to the saturated liquid state to saturated vapor state, and it is achieved, this change of state is achieved through a paddle wheel arrangements. So, schematically we can draw a piston cylinder assembly which is coupled with a paddle wheel arrangement. So, basically we are stirring this water. As a result, we are introducing entropy into the systems, and through this entropy, when we are introducing the systems, or there is some work transfer which is done into the systems, by virtue of which the change of state has happened from saturated water to saturated liquid. So, for this, the first thing that we are going to calculate the work done and entropy produced. To calculate the work done, we have to recall energy equation, energy balance equation from the first law, that is delta U is equal to delta U plus delta kinetic energy plus delta potential energy, that is equal to Q minus W. Now, here one thing, the assumption that we have, it is an insulated container. So, that is delta Q is 0, but there is work transfer and there is no kinetic energy, no potential energy. So, the specific work can be now written as W by m U1 minus U2, the first expression. Similarly, we can get the second expression for entropy balance. So, we start with this expression as delta S is equal to integral of delta Q by T from 1 to 2 plus sigma. Here there is no heat transfer into and out of the systems. So, it goes to 0. So, we can write sigma by m. So, we can say m, or you can say m into S2 minus S1 is equal to sigma, or sigma by m is equal to S2 minus S1. Now, our main intention is to calculate what is this U1, U2, S2 and S1. So, for that we have to use steam table data. So, in the steam table, so we can say 150 degree centigrade saturated water, we can find out U1 as 631.88 kilojoule per kg Kelvin, and again for this case S1 is 1.4848 kilojoule per kg. Sorry, this is kilojoule per kg and this is kilojoule per kg Kelvin. then we have 150 degree centigrade saturated vapor. So, at this state we can find the data from the steam table, which is U2 is 2559.5 kilojoule per kg and S2 is equal to 6.8379 kilojoule per kg Kelvin. So, from this we can now find out what is W by M is equal to U2 by U1 minus U2, that is minus 1927.82 kilojoule per kg, and sigma by M is equal to 4.9961 kilojoule per kg Kelvin. So, what we see from this data is that this work transfer is negative. So, which means that work is being fed into the systems, but the entropy is positive. So, that means entropy is always entropy production is always greater than 0. So, this satisfies this fact that through a steering wheel mechanism it is possible to change the state of water, which is initially saturated at 150 degree centigrade, and we can move to the saturated vapor through a paddle wheel arrangement. Now, the next problem is about the entropy productions for a control volume. Okay. So, the data which is given that air enters a device at a temperature 21 degree centigrade, pressure 5 bar, and separate streams of air at 1 bar leaves the device at one at temperature minus 18 degree centigrade, other is at 79 degree centigrade. So, schematically if you represent, this is your device, there is one inlet for which temperature enters at 21 degree centigrade, pressure at 5 bar, but the air leaves in both the states 2 and 3 with pressure 1 bar, but temperatures are different. The one is at hot outlet is at 79 degree centigrade and cold outlet is at minus 18 degree centigrade. So, since some mass is entering and leaving the systems, we say it is a steady flow device, and we can say make a system boundary as this, as shown in the dotted lines. So, what assumption that we are going to say is that there is no heat transfer and there is no work transfer through this control volume. So, two fundamental equations is required. One is mass balance, which is m1 dot is equal to m2 dot plus m3 dot, and entropy balance equation can be written as m1 dot S1 minus m2 dot S2 minus m3 dot S3 plus sigma dot Cv is equal to 0, because we have through boundary work QCV is 0. Now, also there is another data, it is observed that 60% mass entering the device leaves at lower temperatures. So, from this we can say your M2 dot is equal to M3 dot is equal to 0.6 of M1, M2 dot is 0.4 of M1. Right. Now, when I put these equations here, these equations can now be simplified as M2 dot S1 minus S2 plus M3 dot S1 minus S3 plus sigma dot Cb is equal to 0. By putting these two numbers, we finally get the expressions from sigma dot Cb is equal to 0.4 M1 dot S2 minus S1 plus 0.6 M1 dot into S1 S3 minus S1, and we can bring this M1 here. So, we say sigma dot Cb by M1 dot now becomes 0.4. Okay, this S2 minus S1 can be written in terms of Cp ln T2 by T1 minus R ln T2 by P2 by P1 plus 0.6 Cp ln T3 by T1 minus R ln P3 by P1. So, all the data is given. So, we have Cp is equal to 1.005 kilojoule per kg Kelvin, R is 0.287 kilojoule per kg Kelvin. We T1, T2, P1, P2 are given. So, T1 is 294 Kelvin, T2 is 352 Kelvin, T3 is equal to 255 Kelvin. So, and P1 is equal to 5 bar, P2 is equal to P3 is equal to 1 bar. So, by putting all the data, we can find out sigma dot Cb by M1 dot is 0.454 kilojoule per kg Kelvin. So, this also says, and this term is greater than 0. So, we can say entropy productions from this device is a positive quantity. So, in other words, it gives the feasibility of existence purchase for such a device. So, we have solved two problems, one on entropy balance for closed systems, other is for control volume. So, with this we come to the end of entropy. Thank you for your attention.